We live in a world full of waves: sound waves, water waves, light waves, microwaves, lots and lots of waves. So the better we understand them, the better we understand the world in general. Waves have certain behaviors and characteristics that are particularly distinctive. They reflect, they refract, but they also diffract. Diffraction is what happens when a wave hits an obstacle or goes through a slit. It's the spreading out of a wave around an obstacle or the spreading out of a wave as it goes through a slit. We can represent waves with a series of lines called wavefronts. These are the peaks of the wave. After diffraction, straight parallel wavefronts will become curved, as you can see in this diagram. But what does that mean for real life? How exactly does that affect us? Let's go back to the days when you were playing hide and seek with your friends. Maybe you still do. I know I would. But let's also say that you're not very good at hiding and you decide to hide behind a large tree. When the seeker shouts, "Ready or not, here I come," you can hear his voice quite well. But why? It might seem like an odd question. Of course you can hear his voice. But that's only because it's what we're used to in our everyday lives. Imagine for a second that instead of a sound wave, light waves came out of the seeker's mouth. From behind a tree you wouldn't hear it because light travels in straight lines. Well, all waves, including sound waves, actually travel in a straight line. So why can you hear it? It's all because of diffraction. Sound waves have relatively large wavelengths. They're really big waves. And because of that, even large objects and slits cause them to diffract. So the objects in a forest, trees, shrubs, unsuspecting kids, cause the sound waves to spread out around the gaps and reach you behind the tree. If it wasn't for diffraction, you would hardly hear anything at all. Light has a much smaller wavelength, and because of this, a much smaller slit is needed for diffraction to happen. But if you have a door with a ray of light coming through a tiny gap, and you make that gap small enough, you may see the ray spread out. And if you're behind a couch, you'll find that it's not as pitch black as you would expect. Even water waves diffract. When we use a ripple tank in physics, we see some of the same diffraction patterns that we see with lasers when we're studying light. Water waves will spread out around a barrier, so a seawall really does need to be complete to fully stop the waves getting through. When you shine a light through a tiny slit, a spreading out of the light isn't the only thing you see. If you shine the resulting light onto a screen, you might notice a weird pattern. This is called an interference pattern. Dark and light areas one after another in a series of lines. Or if it's a circular aperture, a circular hole, you'll see some concentric circles. It looks something like this and happens due to diffraction. But how can a wave interfere with itself? It might be fairly easy to imagine two separate beams of light interfering with each other. When the peaks of the two waves hit the screen together, or the troughs for that matter, you get a light patch, and when the peak of one wave hits the screen with the trough of another, you get a dark patch. That would explain the pattern. But why would a single beam of light create an interference pattern? The answer to that question comes from a guy called Christian Huygens, a French physicist who proposed the wave theory of light many years before Maxwell took all the credit with his discoveries and equations. Hopefully he wasn't too bitter about it. Huygens' principle states that every point on a wavefront acts as a source of lots of secondary spherical wavelets. The wavefront, a few seconds later, will be an envelope of these earlier wavelets. Or in other words, an otherwise parallel wave can be thought of as being made up of lots of tiny spherical waves. Okay, but how does this relate to our interference pattern? Well, if a wave can be treated as being made up of lots of tiny waves, then those tiny waves can interfere with each other. So a single beam of light, or even a truly single wave, can create an interference pattern after diffracting through a slit or around an object. Problem solved. Diffraction is what happens when a wave hits an obstacle or goes through a slit. It's the spreading out of a wave around an obstacle or the spreading out of a wave as it goes through a slit. We can represent waves with a series of lines called wavefronts, which represent the peaks of the wave. After diffraction, straight parallel wavefronts will become curved. Diffraction is the reason that sound waves can be heard around corners or behind objects. Sound has a relatively large wavelength, so large objects and slits cause sound waves to diffract. Light, on the other hand, has a much smaller wavelength, and because of this, a much smaller slit or object is needed for diffraction to happen. But if you have a door with a ray of light coming through a tiny gap, and you make that gap small enough, you may see the ray spread out. And if you're behind a couch, you'll find that it's not as pitch black as you would expect. All waves diffract, even light. When you shine light through a gap, you see an interference pattern, containing dark areas and light areas, one after another in a series of lines and circles, depending on the shape of the gap. Huygens' principle states why this can happen. Huygens' principle states that every point on a wavefront acts as a source of lots of secondary spherical wavelets. The wavefront a few seconds later will be an envelope of these earlier wavelets. These tiny wavelets can interfere with each other, which is why it's possible for a single wave to produce an interference pattern. Huygens was a very unappreciated guy, proposing the wave nature of light long before more famous Maxwell. Diffraction is one of the most important wave behaviors to understand. Since we're surrounded by all kinds of waves every day of our lives, the better we understand this and other wave phenomena, the better we can make sense of everything we see around us.